In this lecture, we're going to talk about built-in arrays. These are native to C++. However, in prior classes, you may have used templatized arrays and vectors, and honestly, vectors are your best choice of the bunch, but we still have to go over it. So, built-in arrays are fixed-size data structures. To specify the type of the elements and the number of elements required by a built-in array, we declare them using the following format. We've got type, we've got our array name, and array size. The compiler reserves the appropriate amount of memory. Array size must be an integer constant greater than 0. So to reserve 12 elements of an integer array, we would say int c 12. As with array objects, you use the subscript operator to access the individual elements of an array. And you can also use an initializer list, which will create an array of 5 ints. If you provide fewer initializers, the remaining elements are initialized to their fundamental values. If you provide too many, a compilation error occurs. So here, this n sub 5 will create a 5 element array. You don't have to put in the size if it can compute it from there. So, what does this have to do with pointers? Pointers are valid operands in arithmetic expressions, assignment and comparison. C++ enables pointer arithmetic. A few arithmetic operations may be performed on a pointer, plus, plus, or minus, minus. An integer can be added to a pointer and can be subtracted. One pointer may be subtracted from another, and this is usually appropriate only for 2 pointers that point to elements of the same built-in array. So, for example, assume that v5 is an integer, or v has been declared, and the first element is at memory location 3000, and v pointer has been initialized to point to v sub 0. Below is a diagram of the situation for a 4-byte integer. Okay, so we've got a pointer, v pointer, which is initially set to the start of v, and then we also take the address of v and v sub 0, and we can then go on and say, and v pointer equals v. These are 3 different ways to do the same thing, 4 different ways. So here's the trick. The name of the array in C++ is also a pointer to its first element. So, usually 3000 plus 2 equals 3002, but with pointer arithmetic, the pointer is incremented or decremented by the integer times the size of the memory object. So if you have a struct that takes up 8 bytes, 3000 plus 2 would put you at 3016. So here, v pointer plus 2 would put you at 3008 if we have 4-byte integers. So in that built-in array, v pointer would now point to v sub 2. So for subtracting pointers, pointer variables pointing to the same built-in array may be subtracted from one from another. So you could, if a v pointer contains the address 3000 and v pointer 2 contains the address 3008, the statement x equals v2 pointer minus v pointer would assign to x the number of built-in array elements from v pointer to v pointer, in this case 2, and it points to a built-in array again. So, passing a built-in array to a function. The value of a built-in array's name is also a pointer to the first element. So, array name is also equal to the address of array name sub 0, but you don't need to take the address of a built-in array to pass it to a function. You simply pass the name. For built-in arrays, the called function can modify all the elements of a built-in array in the caller unless the function precedes the corresponding array with const. So, to declare an array parameter in a function header, we'd say int sum elements takes a constant array of values and the number of elements. But we can't modify it. The preceding can also be written like this. We have a pointer to an integer pointer values, which is the start of an array, and then the number of elements. The compiler doesn't know the difference between a function that receives a pointer and one that receives an array. The function must, quote-unquote, know when it receives an array versus a pointer, and that's based on your own semantics. The compiler converts a function parameter for a one-dimensional array to a pointer. Both forms are interchangeable for parameters. So now, taking that using STL, we can sort an array with the STL function sort. We can sort an array of strings called colors with sort colors.begin to sort colors.end. The array class method, begin and end, tell the sort function to sort the whole array. Sort are applied to built-in arrays as well as to internal STL functions. To sort them using built-in arrays, we, instead of calling the array begin, we have to do it the other way. We call begin on the array and end of the array. The begin and end functions each receive a built-in array as an argument and return a smart pointer that can be used to represent ranges. But we'll get back to more. Built-in arrays have many limitations. They cannot be compared using the relational and equality operators. You must loop through each element and compare them. They can't be assigned to one another. They don't know their own size. Typically, a function will receive both the size and the name, and they don't provide anything approaching automatic bounds checking. You must ensure the array access expressions use subscripts that are within the bounds, or else it'll blow up on you. So, as a result, some of the most common security exploits in code target built-in arrays. There are cases when built-in arrays must be used, such as the processing of command line arguments. You should bind command line arguments to a program by placing them after the program's name when executing, such as dir/p. And we can access them by using the argv pointer in your main function and the argl pointer to give you the argl operator to tell you the number of arguments. So, to determine the number of elements in a built-in array, use the following expression, which is evaluated at compile time. The size of the array divided by the size of the first element of the array. The expression divides the number of bytes by the number of bytes in the built-in array's 0th element. For vectors or STLs, we have the count function. Much easier. Pointers can be used to do any operation involving array subscripting. So, for example, assume the following declarations. We create a 5-element array B and a 5-element and a pointer called B pointer. We can set B pointer to the address of the first element with the statement B pointer equals B. This is equivalent to assigning the address of the first element as follows. B pointer equals the address of B sub 0. Built-in array element B sub 3 can be alternately referenced by the contents of B pointer plus 3. The 3 in the preceding expression is the offset. This notation is referred to as pointer offset notation. The parentheses are necessary because the precedence of star is higher than that of plus. So just as the built-in address array element can be referenced with a pointer, the address of B3 can be written with a pointer. The built-in array name can be treated as a pointer and used in pointer arithmetic. For example, star B plus 3 also refers to B bracket 3. Similarly, you can go the other way. B pointer 1 refers to B of 1. This expression uses pointer subscript notation. So here's some code to actually kind of demonstrate those points. Here we have our array B and a pointer which we initialize to B. And then we loop through and print all the elements the way we're used to. Then we actually loop through and print all the elements using the contents of the pointer, or the contents of the array name plus the offset. Now we do it using the pointer with pointer subscript notation. And then finally, we actually use the pointer and the offset to print the array. If we run it, it looks like this. Pretty straightforward. So, there are things called pointer-based strings. We can use C-style pointer-based strings, which we'll simply call C strings. C++ string class is preferred. I mean really preferred. It eliminates many of the security problems that can be caused with C strings, and it's easier to use. We just cover C strings for a deeper understanding of arrays. If you work with legacy C and C++ programs, you're likely to encounter pointer-based strings. Otherwise, avoid them. So, characters are the fundamental building blocks of C++ source programs. A character constant is an integer value represented as a character in single quotes. The value of a character constant is the integer value of the character in a machine's character set. A string is a series of characters treated as a single unit. It may include letters, digits, and special characters, such as minus, plus, etc. String literals or constants are written in double quotation marks. Pointer-based string is a built-in array of characters ending with a null character. And that's how we know the length of the string. A string is accessed via a pointer to its first character. The size of a string literal is the length of the string character, including the terminating null. So we can use string literals as initializers. They may be used in the declaration of either a built-in array of characters or a variable type const char star. That is more common. String literals exist for the duration of the program and may be shared if the same string literal is referenced from multiple locations. That's what the compiler does to make things work a little faster. Character constants can be used as initializers. When declaring a built-in array of char to contain a string, the built-in array must be large enough to store the string and its terminated null character. Accessing characters in a string. Because the C string is a built-in array of characters, we can access individual characters in a string directly with array subscript notation. A string can be read into a built-in array of characters using stream extraction with cin. The setW string manipulator can be used to ensure that the string read into the array does not exceed the size of the built-in array. This applies only to the next value being input, which brings up a problem with strings. If you have a line break or something or a space, it will treat it as a separate string. So instead, you'd use cin.getLine. If we want an entire line, then it'll go up to the return. And it will be stored as an array of characters and length with a delimiter. The function stops reading when the delimiter character /n is encountered or when the end-of-file indicator is encountered when you're reading from an actual file. So to display C strings, the characters are output until a terminating null is found. Cin and cout assume that built-in arrays should be processed as strings terminated by null characters. They do not provide similar input and output message processing for other built-in array types. So later we're going to introduce dynamic memory management with pointers, which allows you to add execution time to create and destroy objects as needed. Improperly managing this process is a source of subtle errors. We'll discuss smart pointers, which help you avoid dynamic memory management errors later by providing additional functionality by native built-in pointers. So this was an overview of how to use built-in strings. And now that we've talked about it, don't do it.